The GYM has a long history through CCAMLR activities. It is a simple population dynamics model that projects stock abundance, biomass, and yield in each age class forward in time. It has now been recoded as an R package, the Grym, which increases its transparency, flexibility, and general ease of use. Installation and use instructions are available at this URL. It is important to note that the Grym can be used to model the population dynamics of any species, but that this video focuses on Antarctic krill. Before describing what the Grym does, a few concepts need to be defined. Let's consider a krill population. Over time, its individuals will grow. Its individuals will die, either from natural causes, such as predation, or from fishing. Once large enough, individuals will become mature, as shown here in red, and spawn. As a result, once a year, new recruits will join the population. Because the relationship between spawners and recruits in the real world is not well understood, the number of recruits added annually in the simulated population is determined through a stochastic process. The Grym accounts for the progression of time by tracking the number of individuals through annual age classes. For example, individuals currently in age class 3 will move to age class 4 at the beginning of the new year, and the same applies to all age classes. At any point in time, the biomass of the population corresponds to the sum of the weight of its individuals. More importantly, the spawning stock biomass corresponds to the sum of the weight of its mature individuals, those individuals that, in nature, are essential to the replenishment of the population and should not be overfished. Simulating the changes in spawning stock biomass over time is the main task of the Grym. In order to assess the impact of fishing, the projected spawning stock biomass must be compared to a baseline, the estimated average biomass prior to the beginning of fishing operations. This unfished virgin spawning stock biomass is denoted SSB0. SSB0 is estimated by averaging repeated simulations of an unfished population under the same conditions as the fished one, including mortality, recruitment, and maturity. Over time, the spawning stock biomass decreases due to mortality and increases due to recruitment and the growth of individuals. Large biomass fluctuations seen here are due to recruitment fluctuations. After 20 years, the spawning stock biomass can be compared to SSB0. In this case, the final SSB is 85% of SSB0. In addition to this final state, another metric of interest is the minimum SSB, reached here on year 15 and corresponding to 64% of SSB0. These two metrics, which we could refer to as the final state and the minimal state, form the basis of CCAMLR's decision rules, used to determine sustainable yield. These rules specify constraints on yield so that both the final state and the minimal state of the population fall within reasonable bounds. Instead of looking at SSB as a proportion of SSB0, the ratio of SSB over SSB0 is used to represent the state of the spawning stock biomass. Depending on the context, this ratio may be referred to as relative biomass, escapement, or more commonly stock status. The two metrics mentioned earlier may now be referred to as final stock status and minimal stock status. We will get back to this later to describe the decision rules used to determine sustainable yield. Which brings us to the word yield. Yield is the biomass removed from the population by the fishery, and in the Grym it is expressed as a proportion gamma of the estimated pre-exploitation biomass B0. Let's go back to the example showing a projection of SSB over time. This particular projection was made with a gamma of 0. No fishing occurred during this projection. The Grym will then repeat this projection while using different gamma values, hence producing different final and minimal stock statuses for each gamma value. In order to account for all the sources of variability and uncertainty, such as recruitment, maturity, and selection by the fishing gear, 10,000 projections are executed. As a result, 10,000 values of final and minimal stock statuses are produced for each gamma tested. This brings us to CCAMLR's decision rules. This Constable et al. 2000 schematic provides a visualization of the decision rules used to determine sustainable yield. First, note that this schematic corresponds to the frequency distribution of stock statuses from thousands of projections for a given gamma. Let's say gamma equals 0.1. The first distribution corresponds to the potential unexploited biomass. At time 0, prior to the commencement of fishing, it has a median of 1, and due to variability and uncertainty, some projections might start from an SSB that is higher than SSB 0, while others might start from one that is lower. The two other distributions correspond to the minimal and final stock statuses we discussed before. The distribution of minimal stock statuses corresponds to the lowest value reached in each projection across years. It can be viewed as a collection of worst-case scenarios. This distribution is used to assess the first decision rule. The first decision rule requires finding the gamma for which the probability of the stock status dropping below 20% of the pre-exploited median level over a 20-year harvesting period is 10%. In this schematic, 10% of projections are below 20% of the pre-exploited median level. These projections, under a gamma of 0.1, comply with the first rule, resulting in the determination of gamma 1. That first rule would be broken in simulations with a higher gamma, since more than 10% of projections would fall below the 20% threshold. The last distribution corresponds to the distribution of final stock statuses after 20 years of fishing under a gamma of 0.1. The second decision rule requires finding the gamma for which the median stock status is 75% of the pre-exploited median level after a 20-year harvesting period. These projections under a gamma of 0.1 comply with the second rule, resulting in the determination of gamma 2. That second rule would be broken under higher gammas, since that median would be lower. In this simple example, gamma 1 and gamma 2 are equal, which is rarely the case in reality. Usually, the two gammas are different. In the case of krill, because there are large fluctuations in biomass due to large fluctuations in recruitment, gamma 1 is often smaller than gamma 2. The last decision rule simply requires taking the lowest of the two gammas to compute sustainable yield. Sustainable yield will be computed using the determined gamma once an estimate of B0 is obtained, for example from the analysis of acoustic survey data. Now that we know what the Grym does, let's take a look at how it does it. What follows will only be a brief overview, and more detailed explanations are given in other tutorials and documents. As mentioned before, simulated individuals are tracked in time through age classes. The structure of the Grym revolves around matrices, where one dimension is time and the other is age class. These matrices, which contain variables such as the number of individuals or the biomass, are solved each year. In the case of the number of individuals, everything starts from a number of recruits. Within a year, that number of individuals will decrease due to mortality, until reaching a final number for that age class. The next year, that number is reused to initialize the next age class. The decrease in the number of individuals is then calculated for that age class from that starting point. And the process is repeated annually until the last age class is reached. Now this is what happens for one cohort or group of individuals belonging to the same recruitment event. In reality, recruitment occurs every year, and every year cohorts move to the next age class. Seen from a different perspective, here is a cohort progressing through time. And here are several cohorts progressing through time with a constant recruitment. Each cohort can be tracked by its color. And here are several cohorts under variable recruitment. In addition to the matrices that are updated annually, such as the number of individuals or the biomass, some static matrices are also computed, such as age, length, and weight. Age increases within each age class in daily increments. After applying a seasonal adjusted von Bertalanffy growth model, the length at any time in any age class is set. Similarly, using a length to weight relationship, weight is set. Knowing the number of individuals and their weight enables the calculation of biomass. By summing the final biomasses of all age classes in each year, the changes in population biomass from year to year may be retrieved. This concludes this presentation of the Grym. As indicated earlier, other tutorials and documents are available, and this URL is a good starting point for anyone interested.